All right, so we've got a quiz on Friday. Um, we'll have a homework due on Wednesday at 7 a.m. I have my usual office hours all this week. I'm just going to write down, so Monday, office hours 1:15 this afternoon to 3:15 p.m. If you need help and you can't make these hours, please make sure to reach out to me and we can try to get a different time that'll work. I met with somebody by Google Meet this weekend, so I'm happy to do that sort of thing. If you need extra help, don't suffer in silence. Also, you can go to the tutoring center. Lots of things. Okay, and so questions on what we're doing in the class so far. All right. So what we're going to talk about today is let's go ahead and review rate mechanisms, right? So we talked about mechanisms for reactions. Okay, and so reactions occur based on a set of elementary steps. All right, so what we can think about is, let's say we have a reaction, A plus B goes to C plus D. Or let's say we have a reaction where, we go A plus B goes to C plus D. All right, and so what might happen there is we might have A makes something called X, all right, some other reactant or intermediate, and then X reacts with B to make C plus D. All right, that might be our overall reaction. And if this is the slow step, so we'll have these various steps. This is the overall reaction. And these are our elementary steps. Okay, that first reaction might be slow and the second reaction would be fast. And there will be always, or almost always, a slow step. It is very rare or very improbable that you would end up with two steps that could be the same speed and slow. Okay. Steps will be slower than other steps, but the slowest step is usually what really determines our reaction. And so I can write a rate law for this. So I'm going to use my overall reaction in terms of defining that rate law. So I could say that the rate of disappearance of A, so how much A changes, concentration of A changes over time, over the change in time. I could have picked any of those things, okay, and done that, but I want to represent that as well so you're not confused by it. Is equal to some rate constant K times something using that slow step. Now I use the slow step to write the rest of the rate law if I know what the slow step is. Okay, and it will be given to me, or we'll learn a little bit later on today how you can determine what the slow step is. What would I write? So the rest of my rate law. What is it? K times concentration of A, right? The reactant or reactants of my slow step. All right. If there were two A's in my slow step, I would then put a 2 there, right? That 2 A's in the slow step means 2 A's have to collide to make an X or something like that. I'm not going to do it, but keep that in mind as well. Questions on how that works? because we're about to move on to something more complicated that uses it. Okay, all right, so that's how we can figure out our rate laws. Now, so far, I've been careful, and your book has been careful to never give you a slow step that isn't the first step, all right? And that's because the math gets difficult. But there's a somewhat simplified case that we can use, something called the steady state assumption, to work with slow steps that are not the first step. And what it says, when I have a reaction, when I have a set of reactions, where the first step is a fast equilibrium. Okay, we haven't really used equilibrium much, but it means that it goes both, it can go forward and reverse, and it does that fast. And the second step is slow. We can assume that the products of the first step are constant, the concentration of products. All right, so let me give you an example of this sort of thing. So we can say that we've got, let's say I have 2A plus B goes to make C. This is my overall reaction. All right, and the steps to make that are 2A go to make an X. Okay? But that's an equilibrium. In chemistry, when we talk about a reaction go backwards and forwards, we use these half arrows, we'll call them. Instead of double-headed arrows, they're single-headed arrows. And so the forward reaction has a rate constant that's K1. The reverse reaction is going to have a rate constant K negative 1. That's my first step. And that is fast. All right. And then my second step is X plus B, let's say, reacts to make C. And that's slow. And we'll give that a K2 for rate constant. All right. So what we've got here then, let's go ahead and write our rate law. Our rate law is going to be rate is equal to, so the rate could be the appearance of C, how fast we get C over change in time. And that's equal to some constant times what? I need to use my slow step here, right? Concentration of X, that's not everything, times the concentration of B. All right. But there's a problem here. So that's great, I've got it. I've got a nice rate law there. But there's a problem here that the way chemists work, if you're trying to do kinetics, is you throw in stuff into a reaction, you watch it react. And you know how much of each thing you threw in. I know what my starting concentrations are. That's easy. So I can know how much A I started with and how much B I started with. And I can use that to try and figure out a rate constant, but I don't know anything about X. I don't know how much X gets made. I don't know how much I threw in, right? So how can we rewrite this, do some algebra, and express this in A and B and get rid of that X? That's what we need to do. And the argument here is that this is fast, right? And this is slow. So X gets used really slowly here. So we can ignore this. And the concentration of X is going to be dependent on how fast this is made and how much it breaks down in that way. Okay? And we're making the steady state assumption that this gets to what we call equilibrium, and this is not changing, at least at the beginning of the reaction. And so we say that if we think about the rate of formation of x, okay, that's going to be equal to, well, dx over dt, if I wanted to write it like that. And that's going to be equal to k1 is the constant that goes to the arrow pointing at x, right? Making x, times, what are my reactants to make x? 2a, so I put an a here, and what do I do the 2? Becomes an exponent. That's the rate of formation of x. The rate of breakdown of x is going to be equal to minus x, right, over t, times k negative 1 is the one pointing away, right? Times what's the reactant for the breakdown of x? For this reaction right here. X. All right. Our steady state approximation says that these are equal. That the rate of formation is equal to the rate of breakdown. So I can set this and this equal to each other. So let's go ahead and do that. So I can say that K1, K1 times A squared, that's the rate of formation of X, is equal to K minus 1 times X, right? And what I'm looking to do here is solve for X so I can figure out what X is in terms of all this other stuff and substitute it in and get rid of my X. All right, so I can do that pretty easily. I can take this and divide both sides by negative K1. Remember, these are little k's.
Do you have to move the negative change in x?
I'm not going to worry about it. We're going to set them, we're setting them equal to, no, don't move the negative. That's a good question. Do I need to worry about this negative? So what you could say is the rate of formation, you'd have to make one negative anyway. The rate of breakdown is going to be, rate of formation of X is going to be positive, right? The rate of breakdown is going to be, it's going to be a negative change. The negative would actually make it positive, if that helps. Otherwise, just don't worry about it. Okay? So we're going to go ahead and do that. And so now I know that, do you see that X is now equal to this, right? And this then can go up into there and I can rewrite it. Okay, so let's go ahead and rewrite it. Actually, I'd like to have both on the screen. I'm going to rewrite it over here, okay? So I'm just going to say rate. I'm not going to do a D whatever because I just want to save the space. Is equal to K, my original rate constant, right? Times K1 over K negative 1, all little k's, times A squared times B. Okay? So I'm taking this here, I'm substituting that in for the X, and then I get this. Now I'm about to do a trick you maybe haven't seen before, so I'm going to stop here. Do people have questions? You guys all, this make sense? All right, so here's a trick you may or may not have seen before. That's a constant, right? Times a constant, divided by a constant. What's a constant? A constant times a constant, divided by a constant, multiplied by a constant, raised to some constant, whatever constant, added to a constant is a constant, right? So I can just squish them all together and make them one constant. Okay, I did more than that, but I gave you more things to it. But if you take any number of constants and you just kind of smash them together, whatever operations you're using, you're going to get a constant out. So we can simplify this and just say that the rate is equal to some constant k times A squared B squared. Okay? Yeah.
So is that not the same thing as like looking at your reactants and products for your two different like steps of your equation and like combining it into the like the overall equation for the entire process and then making a rate law based on that?
Okay. So you can, so a couple things there. So I can add these up, right? If I add these reactions, if I add my elementary steps up here, what should I get? Yeah, I should get this, right? If I add these steps up. But this, actually in this case, it turned out to give us the same thing, didn't it?
Yeah,
Right? That
that's
worked
why I
with
was
the
asking.
overall equation. Didn't realize that. It's not always going to do that.
Okay.
Okay. I have another example where I think you're going to get a half. I don't think we have time to work it. But remember how we had one problem earlier on, like a few lectures ago, where the rate law was at the exponent was actually a half. This is how you can get halves out when you're doing this sort of thing. Okay. So questions? That's a great question. Don't be confused by the fact that it actually ended up being just the overall reaction. But
When you like, can you scroll down for a second?
Yeah.
I just had a question about like the K1 and the K minus one. Like, do those just go away? Like, because like they're opposite signs, so those are just like.
they're not going away. I multiplied, this is a number, that's a number, that's a number, but they're all constants, and I multiplied them together and divide, so they actually end up being a constant. They're not, bless you, they're not opposite each other in value. So let's go, that's a great question. So if we look at this reaction here, these are not likely to be equal, very unlikely they're equal. And this, so if this is bigger, much bigger than this, at equilibrium we have a lot more x than a. And if this is a lot bigger than this, at equilibrium, a lot more A than X. But they're not going to be equal. One of them will be faster, probably much faster than the other. Yes?
So instead of, do you have to go through the algebra or can you just say that x is like when you're plugging the thing in for x, can you just say it's geometrically proportional to whatever it is with a? Like to the rate for a. If that makes any sense, like I know that x would be, the concentration of x would be equal to a squared. So can I just not automatically plug a squared in and know that all the constants combine? Or is that going to mess me up down the line?
I think down the line that you end up with problems with that won't work really well.
Okay.
So let me have you hold on to that.
Okay.
I actually haven't worked the other problem I have that I think gives us a half, but maybe we'll have time to look at that at the end. Otherwise, maybe I can send out an email related to that. These are good questions. And I hadn't realized, my other class didn't catch it, that I picked an example where where when we did the algebra, we ended up with the same thing as this. Okay, that's not always going to be the case. Okay, so let's go ahead and move on, and then maybe we'll come back to another example of that at the end. I do have a second example. But what I want to talk about now is we can talk about energy and rate. Energy and rate. Okay. So we're going to talk about, this is where we can actually get some information. If we have the right information, we can actually make up rate laws. We can actually think about what's the slow step and what's the fast step. And so for an initial example of that, I want you to consider a reaction where I have, let's say, hydrochloric acid reacts with hydroxide ion, and that's going to make chloride ion plus water. Okay, so these would be aqueous, 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 and water's a liquid. All right, yes?
Those are H's.
Yes, those are H's. HCl, H2O. Okay. All right, so what we could think about is this reaction occurs like, I'm going to draw it a little bit differently. I've got a hydrochloric acid where the H is coming over and it's going to run into an OH. I'm going to draw my OH the same. And what that can do is get us to what we call a transition state, where they come to bump into each other and that H is kind of bound to the chlorine and it's kind of bound to the hydroxide at the same time. And the negative charge is actually going to kind of be moving between them at that point. All right, so I've got that H kind of halfway between the two. And that's a really kind of high energy state. That is the highest energy state in this reaction. It's where, because the H doesn't want to be not bound to something. And then our products end up being our chloride ion plus our water. I'm going to do our water HOH, same as H2O, but you see that the water kind of went on to the hydrogen went on to the hydroxide there. All right, I can represent this with what's called an energy diagram. And that energy diagram would look something like this, and we'll use these in a number of different contexts. So we can talk about the progress of reaction. In this direction, okay? There are no units on this. This bothered me when I was an undergrad. That this is the progress of reaction, no units, it's not time, it's not anything, it's just how far the reaction has gone. And then over here we have potential energy. Okay, and so for our reaction up above, we might have the energy of the reactants. So our reactants are HCl and hydroxide ion, right? That's what their potential energy is. And down here, after the reactions happen, now we have water and we have chloride ion at a lower energy. And in fact, the change in energy for this reaction is negative 79.9 kilojoules per mole, which is a lot. Okay, so it's fairly spontaneous reaction. It's giving up potential energy. That's what makes things spontaneous. And so what it would look like is this. Okay, we'd have a reaction path in terms of energy. So this HCl is going to start giving up its H, and the hydroxide is going to start taking the H. And as we do that, the energy of the system goes up and up and up and up. So we're kind of in the middle here, and then it comes down as the H goes to the OH. And so this part right here, this is called the transition state right here. We give it a double dagger, and that double dagger is right here. So this thing is right there in terms of thinking about the energy. Questions on that conceptually? So to get from reactions to products, we have to get over an energy barrier. Okay? We have to get over an energy barrier to get there. And that energy is called the activation energy. So let's say we take the difference here. This is what we would call EA, okay? And that is the activation energy. And so let me go ahead and type out what that's a new term. We're going to type it out down here. Activation energy is the energy that reactants need to acquire to become products. Okay, a more precise way to say it is, or another way to say it is, it's the barrier they need to get over to become products. Does that make sense? Okay. And if we look at this, we have this change in energy for the reaction, right? That's 79.9 kilojoules per mole. If I take this out and that out, that's the difference. This is the difference in energy between the reactants and the products. So this is going to be that delta E from up above. Questions? Does that make sense how those all fit in? Okay. So let's go ahead and let's look at another example of this. So here what I have, let me put both of these in the same place. Here I have a reaction. And this has 2 steps instead of the 1-step reaction I was showing up above. And it makes an intermediate, okay? What the intermediate is it's something that's semi-stable, let's say. It's got fairly high energy, but it's more stable than the transition states. All right, so what I've got here is I've got these reactants. I've got this compound, some methoxy, I'm not sure what to call that, chloroformal something. And they're going to make this intermediate. So this is going to stick to this to make an intermediate. Okay? So they're all together in one, and then the intermediate's going to fall apart in a way that it kicks out the chloride. This is something you'll do in organic. All right? And the transition state, there's a transition state between here and here. And there's a transition state between here and here. They're shown on here. All right, so if we look at if we look at this intermediate, its energy is right there. Okay, just where it says intermediate. And this is the activation energy to get from the reactants to the intermediate. And then this is the activation energy to get from the intermediate to the products. Okay? Do you guys see step 1, step 2? Okay, what's the slow step? The first one, right. It's the first one because the first one has a higher activation energy. All right, so let's go ahead and let's write that. The first reaction is the slow step. Okay, so it's a slow step because it has the higher activation energy. What's the rate law for this look like then? Go ahead and try and write the rate law real quick. Okay, so hopefully what you wrote down was we've got a rate, and that's going to be equal to, this thing is H, O, and Cl, right? So it's going to be, let's see, H isn't coming off, CHOCl, okay? The concentration of that times a rate constant K times the methoxy concentration. Because that's my slow step, and those are my reactants in my slow step, and there's one of each. That makes sense why we did that? So I've got a practice problem down here.
Is there any reason you wrote the O like after CH3O?
That's the order you write these things in. So you write, I don't know that I'm gonna care that much. So the way, it's a good question. So, but in organic you'll get this down more, but you always write the C first. then you write the H's, how many H's, then you write how many of, it might be actually in order of the periodic table except the H, in terms of going left to right. I'm not sure I even know what the rules are, I just do it. But if I have a CH and O, I put them in this way, and then these halogens usually go last, the fluorine, chlorine, bromine, etc. So let's say it's because you write the C, then you write left to right on the periodic table. And when you get to organic, they can fix that. They can fix that and tell you what the right way is if I made a mistake there. Okay, so moving on, let's take a look at this reaction. So we've got some reaction here. What I'd like you to do is make up. I want you to make up a reaction that's consistent with this. Okay, that's not part of their problem. Make up a reaction, draw however many steps you need to make something consistent with this. Okay, and then do the energies. And you see the energies are on the side there? We've got energies on there. So the first thing is, how many steps is this reaction going to have based on what we see? It's going to have 2, right? 2 steps. We've got 1 step to get from here to here, and then another step to get from here to here. So 2 steps, make up something with 2 steps, and then figure out what the energy is for each step. What does it want? The activation energy for each step, and then the overall energy change.
Are you talking about like A, B to C to D, or are you talking about like actual stuff?
Well, AB, I would do AB. I'm going to do AB. But you could do actual molecules if you want. I won't do an actual reaction because I don't know that it matches this in terms of the actual energies. Yes, kilojoules. All right, why don't we go ahead and do this? So I'm pretty lazy. I'm going to make an easy reaction. I'm going to have A. I'm going to make my overall reaction as A. That's my overall reaction is A to B. I'm going to make A turn into X. I'm going to make X turn into B. Okay. A has to do some sort of transformation, and then to X, and then X turns into B for this. And then, so X is right here. A is right here. B is right here. All right. It's actually asking for the activation energy of each step. So A to X, E activation, so EA, equals what? Yeah, it looks like we start at 40 and we go up to what, 70? Yeah, so 30 kilojoules per mole. Okay. And then the next one, the activation energy of X going from X to B. What's the activation energy? Yeah, it looks like it's about 5 kilojoules per mole, right? We're going from about 55 to about 60. Activation energies will always be positive. So 5 kilojoules per mole. Questions? Do you see what we're doing there? So activation energy 1 is this. Let me give that a 1 and give that a 2. EA1 is this. And EA2 is going to be, well, what? It's even smaller than that. EA2 is from the bottom of this, so we'll have to make an EA2 out there. Questions? Okay. And then it's asking for the overall energy of reaction, right? The overall reaction. So what is the, that's not going to be an activation energy up here. That's going to be a delta E, right? Overall reaction, not EA. What is that? Well, we start at 40 and we go to 30, right? So it loses 10, so negative 10 kilojoules. Questions on that, what we just did? Your reactions may have been different, but you want to be consistent with a two-step thing. Yeah.
Oh, well, the E, we always do the, and then
For the EA or for the activation energy, we'd always use the, you're right, we use the final minus the beginning, right? So if we do the final minus the beginning, we'll get a positive number. Or you can subtract either way, just not if you can remember it's a positive number as well. But do that otherwise. Activation energy will always be positive. You never have a negative hill. And then, right. And then the same thing here. Here we took the final minus, right? Products minus reactants, and we got the final energy. So 30 minus 40 is negative 10. And that's the right way for the sign to go because we went from higher energy to lower energy, we released energy. So it's negative. It's not gain energy. Does that make sense in terms of the signs? Okay. Questions before I move on? It's going to get more mathy even. Yep. All right, so we have an equation called the Arrhenius equation that's going to explain, and it actually has a lot of it is very similar to what our Clausius-Clapeyron equation was. So, but the Arrhenius equation Arrhenius equation explains, predicts, we'll say predicts rate constants, how rate constants change with temperature. All right, and so our Arrhenius equation is going to have this form. We're going to have our rate constant, I'll go back and label what these are, is going to be equal to A. A is it's a frequency factor. It has to do with how often your molecules, when they collide, or on the orientation they can react. So if you think about my pen here, my pen, let's say my pen has to react in a reaction with this molecule over here in this orientation, then it would be very unlikely that, you know, it's going to have that or come in some other orientation. So this is a very small frequency factor, as opposed to a frequency factor where it had to hit the side of the pen. Lots more ways to hit the side of the pen, if that makes sense. That would have a higher frequency factor. So A times E to the negative, there's our activation energy over RT. Okay, where our temperature is in Kelvin. So let's label what these things are. This is your activation energy. This is our temperature in Kelvin. This is our ideal gas constant. And for this, we're going to want our units to come out in joules. So we're going to want the energy version, or that energy version. So 8.314 joules per Kelvin mole. All right. This is our frequency factor. which once again is whether how often the molecules are in the right orientation to react. It's really how often when they hit do they react. They hit with enough energy. And then this is our rate constant. So that's that little k that we've been using over and over again. All right, this is very similar to our Clausius-Clapeyron equation, and we can do similar things to it. It has an e in it, so we can take the logarithm of both sides. So I could have logarithm of k is equal to the logarithm of a times e to the negative ea over rt. All right, but I'm taking the logarithm of something times something else, a times something else. So I can split those up and add them. The logarithm of a plus, if I take the logarithm of e to the ea, the logarithm cancels with the e, right? It's not really canceling, but they go away. Now, let me write that out. So I've got ln of e to the ea rt. These are opposite operations here. So that's going to then give me the logarithm of a plus, well, plus minus ea rt. Okay? All right, so I can go ahead. Yes?
Why are you able to switch the multiplication to
For this, it's a lot right here, right? If you add those together, that's a log property. So it's just the property of logs when you do that. It's one of the things we can do. You wouldn't want me to do the proof anyway. And I actually couldn't do the proof off the top. So what we've got here then is I can rearrange this equation. So I'm going to take one side and the other. I'm going to slightly rearrange it. So I get logarithm of k is equal to negative EA over RT. Hold on. Negative EA over R times 1 over T. Okay. Plus the logarithm of A, which is our frequency factor. And what I hope you see here is that this is in the form of a straight line. Y is equal to m times x plus b. Okay. We did this before with the Clausius-Clapeyron equation. If I was to plot this, am I going to get an upward sloping line or a downward sloping line? Downward sloping line, because my slope here, this is my slope, is negative. So I would end up, if I plotted this, getting a line that looks like that. What is this point that crosses the y-axis? Natural logarithm A, right? It's my b. And what's my slope equal to? That, right? Yeah, bless you. That makes sense? Okay, so that's great, but we're not going to be plotting things a lot, right? So we can plot things occasionally. But like for a quiz or something, I'm going to have you do this with like 2 points, right? We'll use the 2-point version of this equation, which we derived in the last for the Clausius-Clapeyron equation. So remember that I can just I can do anything to an equation as long as I do it to both sides, right? So if this is my E activation over R at times 1 over T, and I've got a K1 and a T1. That's some temperature and some rate constant that go together, plus logarithm A. I could also do it under a different temperature, in which case I get a different rate constant. And I'm doing it with a different temperature. And I should still have the same frequency factor. Like that. Okay? I can subtract these from each other. And this is going to get that 2-point version of the Clausius-Clapeyron equation. All right, so I can have the logarithm of k1 minus the logarithm of k2 is equal to negative EA over R 1 over T1. I'm subtracting, right? Minus this, minus that. So I'm going to then make my next bit is going to be minus EA over R times T2 plus logarithm of A. And then remember, I'm subtracting this one. So we're going to go minus logarithm of A. And now I can simplify doing those log rules we've talked about. Okay, first off, those things cancel, right? Because I've got plus and minus, the same thing. And then over on the left-hand side, if I have a logarithm of something minus a logarithm of something else, that is the same as saying I have a logarithm of k1 over k2. Okay, and then I can factor out, see I have an EA and an EA over here, times this, times that. I can factor that out to give myself negative EA over R 1 over T1. See how this one's positive? Now, once I pull this out, the T1's positive. Over here, when I pull it out, I got that negative. And so the T1 will be 1 over T1, or T2 will be negative. And that's what I get. Okay. Does that, you see how it look like the 2-point version of the Clausius-Clapeyron equation? Pretty close to the same thing? Okay, so now that we've gone and derived that, I'd like you to work a problem. I think I'm going to have to like write out the bits of the problem here. Last hour, people couldn't see it very well. Okay, but this is a problem where what we've got is we have this reaction up here, and the chemist has measured at different temperatures what the rate constant is. And what you're supposed to solve for is the activation energy, so the EA, okay? It says to determine the frequency factor too. We're not going to be able to do it with our, I mean, we could plot 2 points and do it and see where it intercepts, right? But we're not going to worry about that. Let's just solve for the activation energy here. Okay, so here's your equation. I'm going to have you guys do it. I'm going to write your stuff out here. So let's just take we're going to take 2 points off of this instead of plotting like they're doing. I think it's 109.0 is its first point. I think the first temperature, and that's in Celsius, right? So remember that you're going to have to convert for Kelvin. Kelvin is 273 degrees plus whatever your Celsius temperature is. I'm not going to do the conversion for you. 1.90, okay, is our first temperature. Our second temperature, let's have a big change. We're going to pick 14.9. I could have picked any 2 points here, okay? Any 2 points would work. Those are the 2 I'm picking. And then the rate constant in K, it's in seconds to the minus 1 or 1 over seconds, is going to be equal to the one that corresponds to 109 degrees Celsius is 0.00153, and the one that corresponds to almost 15 degrees Celsius is 0.00360. Go ahead and work that. So let's see, we've got about 11 minutes left. Take 3 minutes. Yes.
Okay, so we'll have to do for this one.
Anybody else have questions, Doc?
Just the R 8.3.
Oh, yes. Let me give you the R. The R, you will always be given all the constants and all the equations. And if you feel like you've been shorted an equation on a quiz or something, you should, or a constant or a conversion, you should ask me for it. That's the R we're using. Anybody want a little more time?
Yes.
I know. Do you want it in kilojoules or joules?
If I don't ask, you can put in whatever unit you want. The answer is 178,000 kilojoules per mole.
Oh, yeah. I'm sorry.
That's good.
And this giant stack, I think we handed these out. I actually have my name on them. I guess I think I've handed these out earlier, but if you want to go to tutor, want to make appointments at the tutoring center, there's information for that there. But like I said earlier, I'm also happy to work with people outside of those office hours. Just let me know. We'll figure something out. Okay, let's go ahead and work this one. So what I've got is I've got to get these temperatures converted, okay, to Celsius. So I'm going to go ahead and take 109 times or plus 273. By the way, stop me if you see me make a mistake. This is going to be the temperature in Kelvin. So 382 is what that is, and then I've got 114.9 plus 273. Whoops, I subtracted. 273 plus 114.9, 387.9. I should put a 0 there. Okay, those are my temperatures. I'm going to go ahead, I can just rewrite this down here. Do I need to convert logs for these numbers here? I don't, because they're going to go into this. I divide them and then I take the natural logarithm, right? If I split it up and was subtracting logs, I'd need to do that. I'm going to try and scoot down and keep the equation up there. So let's go. I'm going to go and divide these numbers and put them in. I'm going to do just top over bottom for 1, 2. So if I take 0.00153 and I divide it by 0.00360, I get, yeah, it looks about right. Okay, I've got the logarithm of 0.425 over here, and that's equal to negative EA over 8.314 joules per mole Kelvin. Okay, and that's going to be times 1 over my first temperature is 382.0 minus 1 over 387.9. All right, I can, in my calculator, what I'm going to do is I'm going to subtract these two, and then I'm going to divide what I get by that. So for me, I do 382, and there's a 1 over x key. Okay, I hit the 1 over x key, I subtract minus 387.9, 1 over x equals, and I get my answer. Okay, and then I'm going to go ahead and divide by this, because that's a number that's on top. I'm going to divide by 8.314, and I get a number with a whole bunch of zeros in front of it. So this is now going to become, on this side I have negative EA times 4.789 times 10 to, I think it's a negative fifth. 1, 2, 3, 4, 5. Oh, what? 1, 2, 3, 4, 5, 6. Negative 6. We'll see if this matches, because actually I think this is going to give me a different answer than I got last hour. I'm going to go ahead, I'm going to take the logarithm of this 4.25, and I'm going to divide by 4.789 times 10 to the negative 6. Whoops, 6th. That's going to cancel. So logarithm of something less than 1 is going to be negative, so I'm going to have negatives that are going to cancel as well. All right, divided by 4.789 E6 negative. No, it is the same answer. Maybe somebody had something written down different. Anyway, so what I've got here now is negative 179 kilojoules. Actually, let's do it like this. My straight units out are 1,000 joules, okay, per mole is equal to negative EA, and I can cancel that, okay? And you could put that in kilojoules, so 179 kilojoules per mole. I didn't read the problem carefully, but if I don't ask you for a unit, you don't have to give me, you can give me whatever units you want. You had your unit first.
Okay, so on the second, equation line, did you, for the temperatures, you did the division and then subtracted them?
Yeah.
Did you multiply it by R or no?
I would divide it by R.
Divide it by
Is the R's on the bottom?
Yeah.
Good question.
Thank you.
If you use a different point, do you get a different answer?
You should not? Okay, so that's a good question. Use different points, you get a different answer. If it's real data, yes, because real data is not going to make a perfect straight line. I bet you this synthetic data they made up for the problem, this is perfect data.
Okay.
But for real data in the lab, you want to use all your points and plot it. But for a quiz or a test, all I can do is ask you, I can't do the plot. It's not going to, I can do anything I want, right? But it wouldn't go well. So we take too much time. Other questions? Yes.
So would it be wrong to do the natural log of the beginning?
Yeah,
Divide that beginning at the exact same answer.
it would not be wrong. You could do this in all sorts of ways. You could do this in all sorts of orders and break out the steps however you like. And did you get the same answer?
Yeah, I
Yeah,
got the same answer.
yeah. So it's fine. For a lot of these things, there's lots of different ways to do them. They're all correct.
Okay.
All right. You guys have a great a great couple days and come get help if you need it.